All right, thank you everyone. So we have a few questions. I guess we might go a little bit 5-10 minutes over time, but this is the last session, so hopefully it's okay. And any questions that we may not have a chance to basically answer. So there are still indeed quite a few questions that unfortunately we weren't able to answer, but we'll try to sort of capture some of the salient questions that we weren't able to answer. We're starting perhaps with Thorsten and Gert, with you guys. This question, I think you sort of discussed that already, and this question came in the morning, but we weren't able to answer it. Thought on some standardization approaches to allow minor setting changes or firmware updates to be implemented quickly.
Yeah, I guess implemented quickly is probably difficult because one of the obstacles to doing changes is actually the comprehensive system studies that we have to go through. I think in some cases there were things that could be done, but I think the customer would refrain from changing the control scheme of an already operating plant, for example, because then would require half a year of system studies to get it approved again. So I think that is. It could be good if we could have some a more standardized way of doing these assessments, and maybe if we or the customer could get access to simulation systems of the whole network, where we could easily assess the impact of controller improvements. Because as it is today, we can only get because of IPR issues, we can only get a limited representation of the network. And then we have to depend on the system of the TSO doing comprehensive studies to assess the effect.
Yeah, I come back to that in the last bullet point, but if I understand correctly, essentially saying that it is not any quick way of implementing it, and obviously because you need to do comprehensive studies, and you also need to pay attention that if you're making change compared to the original, then there is no side effect on something else, basically.
Yeah.
So,
may solve one problem.
Exactly. Which brings us to the second point, that essentially the second question, which again, this was from early in the morning, but as you guys are here, I could, if I could ask you to answer this question, is that to what extent are you guys looking at outage conditions when you're designing or tuning your inverter? Is there any optimization applied for non-credible contingencies or N-1, -1, or anything beyond the next credible contingency?
Yeah, and that of course comes, I guess you are the one driving that, and also in other TSOs like ERCOT. I think usually the dimensioning cases that we have to study are usually these N-, I think ERCOT is up to N-6 that we have to consider for SSR studies, for example. So yes, that is usually we'll end up tuning the control system according to some N-1, -1 outage condition. The issue is then, of course, that a lot of the requirements and the performance requirements, they are based on having a good performance in a strong grid. And then we may trade off some of the performance in the N-1, -1 situation. So I think our opinion is that we should probably allow for a little slower set point response, a little slower PLL response, in order to be more robust in these special contingency cases.
All right. Okay. And the last one probably is not directly for you, but as I have you, I'm keen to get your view first, and then we go and ask other people. So what is your view on coordinated tuning of multiple wind farms, some wind, solar, battery, you name it? And in your view, what are the key impediments that it's not done to the extent that it could have been done?
Yeah, I think that is, as you mentioned also here, right? It's the last one who comes in, who has to take the blame for the whole thing, right? That's also what we saw in the Queensland case, right? So I think the first wind farms, they are tuned according to a relatively strong grid, and then the last, and as you connect more and more production, then the last production unit will see a very weak grid in total. But it's not really possible to tune the first wind farms again, because as I mentioned also earlier, then the customer would have to go through all these registration steps, and there's a big uncertainty related to that, so it would be more safe for them just to stay with what they have. So I think if you could make a more open environment where it's easier and less risky for the customer to do a retuning of the plant and maybe pay them to some extent for it, then I think there could be a solution to optimize a whole system that is already installed, rather than just tuning the last one, the last wind farm that came or the last solar farm that came.
All right. Okay, great. So anyone from AEMO or AEMC or TNS want to share their views on this particular aspect? In your view, is it done successfully currently? If not, what can be improved?
So, Babak, I can share from TNSP point of view, and as I presented in my presentation, so definitely there is a merit in looking at system-wide retuning, and this is exactly what has happened in North Queensland, where the existing plants, we're enabling them to retune to maximize the hosting capacity. And I don't want to talk for AMC, but reading at their framework review report, they are definitely considering this as one of the options to increase the system strength of the network.
Right.
It's Julian. Yeah, no, Sachin's right. We have considered it, but we've realised that it's not an easy process, and so we're focused more on more urgent things. But we definitely think that retuning, where it's able to be done, is the easiest way of solving the system strength problem. However, there are quite a range of obstacles so we really would need to look at this in the future, and would encourage others to look at it as well.
Yeah, and I mean, what is that? I understand, Thorsten, you have a point, but I think the other perspective also, definitely there is a point that also part of that is like really willingness and cooperation from everyone, because, and I mean, you guys have a good reason. I think that's part of it, that maybe this is not done to the extent that could be done, that because of your IPs and other manufacturers' IPs, and, to what extent everyone can come in, part of making the same recommendations and applying the same recommendations and solutions and retuning in the network without compromising your IPs that essentially worth billions of dollars and several years, if not decades of experience. And like, I appreciate and I agree that it's a chicken and egg. You need basically modeling information from network and not just your connection point to be able to do your job. But at the same time, if all manufacturers would be also willing to be part of the same solution. But anyway, so I appreciate this is a challenge, but also probably a prudent way of operating and planning power system, that if you have assets that with very little investment can be improved, such that it alleviates or maybe eliminates system strength issues, that would be a prudent way of doing compared to introducing new assets in the network. That was a good question. So sorry, we stay a little bit longer. Moving into the next couple of questions, Abu Talib. I hope you are still there. I appreciate it's very early in the morning. The first question is that in your studies, did you consider grid forming or grid following inverters, or does it really matter?
Can you hear me?
Yes.
Yeah, so basically the answer is that we did not consider grid forming. We considered the type 4 IDRs and type 3. And the reason we didn't, in fact, for some of these operation problems, for example, for power sink protection, grid forming is considered a solution because of the provision of inertia. However, we did not consider, the main reason is because the control modes vary and the models also vary largely, so it's not easy to find one model that can be representative of let's say a large category of these models. So we have not considered it, no.
Okay, all right. So perhaps a little extension of this question, which I haven't written it here actually. It's just and I think that was interesting that in some of your slides you were saying that some of the sort of old-fashioned approaches of implementing the algorithm were more successful or less prone to mal-operation. And I like talking about grid-forming inverters and the question that we had earlier in the morning, that, for example, if we can have a power system all with grid-forming and grid-following and maybe with sync-ons, and definitely less or much less of synchronous generators. So a lot of these protection systems and relays have been designed based on a power system with dominance of synchronous generators in mind. If we don't have such a system, do we need these relays to begin with to be worried about whether or not they will mal-operate?
Yeah, and Steven Sproul here from Hitachi ABB. One of the points I didn't touch on when we spoke about fault contribution from grid-forming inverters is while synchronous machines have a very high peak fault contribution, it's very short in duration. So grid-forming converters can provide fault current for much longer. So although it's less in magnitude, it can be for a few seconds. So there are, we've got experience where you can change protection settings. Some thermal, fuses on distribution networks, they can be harder to blow if you don't have that magnitude, but it's really just a different proposition that you just need to design your protection system to. So there's pros and cons in terms of what they can provide at the moment.
All right, great. Abutaleb, you want to add anything?
No, not really, except that we expect a difference between the fault response of grid-forming and grid-following inverters. We have not specifically studied the challenges of grid-forming inverters on system protection. But some of these behaviors that we described for grid-forming inverters, they also apply to grid-following inverters. For example, the limit on fault current level, the amplitude, because at the end of the day, the fault current is being generated by power electronics. And because of that, it's limited.
All right, okay. So the next question, you're talking about 0% and 25% and 50%. So the question is that what is the calculation or math behind it, or they're just random numbers? Essentially, like, what is the conclusion? Is that, like, I mean, this is just one example. Are we saying that regardless of penetration level, we should not be using RMS modeling because we could get wrong results, or it could be a sort of, I don't know, rule of thumb that could be applied to determine what is behind that 25 or 50%? That down to that level, you could potentially use RMS modeling, and above that, you probably should not. Could you elaborate?
Okay, so here's this. Yeah. So the story behind it is that we wanted to perform a qualitative study. So there is no specific reason behind these numbers. 25. We wanted to increase the level of IDR until we hit a limit where the consistency becomes considerable. So what we saw was that, as I mentioned in the slide, we have an EMT model and an RMS model. So they have modeling differences, especially with respect to modeling of fast transients. So what we saw in the power swing results was that during the first few cycles after the swing, the two models were giving different results due to the different modeling assumptions. But when the swing started to settle and the fast dynamics, they basically died out, the two models were giving consistent results. However, when we increased the level of IDR, the initial modeling differences started to play a more significant role. And at some point, basically, in this case, it was 50%, but it's not a number that applies to all systems. They vary depending on the system. Okay. And I think there was another question regarding at what level of IDR do these problems of power swing start. Basically, the answer is there is no magic number. It depends on the system, depends on the power swing protection scheme and settings. Yeah.
All right, thanks. Okay, moving on. Then 3 questions on grid-forming inverters, which they came quite late last time. And sort of actually it's a good time that we're taking it here because especially the second one that I'm keen also to get views of Vestas. I don't believe we have estimate, but just get views of two OEMs that we have currently. The first question, maybe you can take it, Stephen, first, and if Gert or Thorsten you want to add or agree or disagree. The assumption here was that the grid-forming inverter would be more effective with battery energy storage than a solar farm or wind farm. So especially the reference is to do with tolerance to phase shifts. What is your view?
Yeah, so in our experience, we've always had a voltage source behind the grid-forming converter. So whether that's a capacitor, battery, and we've used flywheels in the past as well. So we do believe in terms of solar when we're providing the inertial response or system strength through fault contribution, because solar is coupled through a MPPT or a current controlled device, that you would need some initial buffering. So you'd need a small cap or some real power voltage source to bridge that gap. So moving forward, we do see grid-forming inverters with a small capacitor or battery DC coupled to solar to get your grid connection, and then you could use that battery for revenue generation or whatever you want to do there. I don't have any experience with wind given the company I work for, so I'll let others comment on that.
All right. Thorsten or Gert, do you want to add anything on that?
Yeah, I agree. What we see, our point was more that we think that we should introduce this grid forming in the wind industry in some steps, because if you are to fulfill all the features that is listed for grid forming, then of course it will be required that storage is part of the solution or some kind of battery or caps. But we are looking into what we can apply also with the existing hardware that we do have, and then of course inertia support and fast fault contribution. Some of the things that is limited with the existing hardware.
Okay, great. Right, and the next question, I gave you a heads up actually that this question will come up, and it did come up. That what is the optimal mix of grid forming and grid following inverters? Are we talking about 100% grid forming inverters in the future or 50%? It's not going to be as easy, but what factors would you consider, and what are there pros and cons, or what needs to be considered?
I'm not sure exactly what is
So,
determined, but if you're looking at the industry or the research that has been done, then the mix between grid forming and grid following, if you are to go for a full penetration of inverter-based resources, then the rate, it's in the range of 25 to 40% that is listed in the studies that has been performed of how much grid forming is needed compared to grid following.
Yeah, all right. Okay, first this one for you, Thorsten. So like the slides that you were presenting, and it was quite interesting. Can I extrapolate that to say that in your view, you cannot achieve a power system with 100% synchronous condensers and grid following inverters only, or you can? If you don't, you can.
Yeah, but I think my point was actually just that you have two different issues. One thing is maintaining the voltage and having a stable frequency, and the other is the transfer capacity limit. You have to consider what is it that you're trying to solve. If what you're trying to solve is that you have a very long, a very remote system, then it doesn't help just to install grid forming inverters or synchronous condensers. That will not increase the transfer capacity. There you need a better correlation between load and production, or you need a more power lines or some storage, right? So I think Yeah, and
Stephen Sprout here, I'd agree with that. I mean, there's there's evidence of, I mean, the Dalrymple system, when it islands, it operates with no synchronous machines. It's just a grid-forming inverter and wind farm, but that's fairly geographically, in a small area. The mix is going to be dependent when you have, large impedances between loads and generation, and you get the pockets of low system strength. That's going to influence that mix of how much grid forming, how much grid following, and even synchronous condensers to get the fault current. So there's no kind of one answer in a small area. You don't need, it's going to change based on the network characteristics.
Yeah, which is consistent with what I was presenting, and like the three factors that you have. One is IBR saturation. The other is the, how many synchronous generators and how close they are, and how scarce they are, or synchronous machines actually. But the third one, which is not probably very widely understood, I'm happy that Thorsten, you had some discussion, is basically network characteristics, and load is also part of that network. So if you have wind and solar and battery in remoter part of network, you're going to have more challenges to be able to not just generate several gigawatts of wind and solar, but to be able to securely transfer that across the network. All right, that's good. So that's really good. Moving on and talking about load characteristics. This is actually a question not related to anything else, but I thought it's a good question, and I'm just rephrasing it a little bit, but it's consistent with the question that we had in the first session. I'm not sure who I asked. Perhaps I'll go with you, Andrew Halley, if you don't mind to share your views as far as like something like electrolyzer is concerned. Is that going to be a positive or negative or no impact on system strength?
I'll take myself off mute, that'll help. Look, it really does depend on the technology that gets connected, doesn't it? My understanding at this point in time is that the sort of containerized electrolyzers that you can purchase at the moment, sort of something between 10 and 20 megawatts, they actually do require some sort of minimum short circuit ratio to operate. So, if you were to just go and buy 10 or 20 of them and put them all on the same site and say, well, there's my hydrogen production facility, that would be a bit of a problem, because that becomes another device that's going to consume a certain amount of the available system strength. But hopefully going forward, as that technology matures and the scale of those sorts of facilities increase, that these issues will be taken into account, and we won't have those requirements. They'll actually be designed to be self-supporting, just like hopefully future wind farms and solar farms and the like. So it really comes down to the technology and where you put it as to whether it's a positive or negative impact on system strength.
Okay, great. Anyone wants to add anything to Andrew's comments? All right, so that is the end of this session, and indeed almost the end of this workshop. My only question is that if any of panelists want to add anything that wasn't opportunity, especially those of you that I apologize we couldn't have any questions for you. If there is anything anyone wants to add, now is a good time. All right, doesn't seem to be any further comments.